So this presentation is kind of a love story between Agda and Haskell. I hope you take it that way. I will present a lightweight approach to verify your programs. But there is a more sinister reading hiding beneath, and it is that I will offer you a gateway drug from the softy that is Haskell to the really hard, addictive stuff that is dependent type programming. And in the world of proof assistance, these substances are abound, like Cockx and Lean, but I will focus on my own part of the world here. So, what's the problem with the current program extractors in Agda, which is called Malonzo? You write a simple recursive function over trees, and then you get this hideous output. It's okay, it's verified because you have a verified source. Well, not completely, but at least you trust it a bit. But you cannot share it with your colleagues. It's unreadable. You cannot say, oh, here it is. It implements the insert function. Use it in your larger code base. You would never be able to do that. And now you say, OK, Agda is a bit more experimental, so let's go to a more mature proof assistant, Cockx. It's lived long enough. It has a much more readable output in general cases. But then you get kind of you write a monoid type class, and you don't get a Haskell type class. You get this intermediate dictionary passing style thing with generated names A1 and so forth. So this is, again, unreadable. So what we want to offer in our work is a new backend to generate Haskell from Agda that has different design goals. It's not really a program extractor for the whole language. So what we want is to write something that looks like Haskell within Agda. We don't have to cover the whole feature set of Agda, so we won't get these unsafe coerces we saw with Malonzo. And do the proving, of course, inside the same system. Right, and this is enabled, at this point in time at least, because Haskell and Agda are quite similar. Again, this love story continues. They are very close to each other. To write Haskell code, we don't need to embed, to have a deep embedding of Haskell, right? So we can just write Agda that really looks similar. It has a very expressive type system using dependent types that can express all interesting properties you can think of. And we have this really cool new feature called runtime irrelevance, or simply erasure, that lets you divide, kind of separate the proof level stuff that you don't want to execute and the actual Haskell code, Haskell-like Agda code. And we have also an extra benefit of intrinsic verification you don't find normally in these kind of tools, and I will get back to that. So let's look at a simple example. We have data type, simply type binary search trees, which holds data at the node, sorry. And we have this insert function we saw. It just navigates to the correct place and inserts an element. And then we compile it, we get kind of identical code, I would say. Yeah, there are double colons instead of single colons. That's not really an issue. The only important part is these arguments here. So under the hood, these are erased proofs, because the compare function that we use in Agda is really calculating the constructive proof that two numbers are related. And that we don't get in the simply typed version we have. All right, and then, okay, this is kind of almost identical code, and then we can extrinsically, or after the fact, prove that this is correct. I don't want you to parse this or understand this. So once you've crossed to the dark side of dependent type programming, you will understand the Unicode art here. But like from a distance, this is kind of, okay, I don't have a clicker anymore. From a distance, it looks like the program we had originally, just with some proofs. And most importantly, we can see these little proofs here. Oh, we actually use them to prove things. And that's where intrinsic verification comes in, because you can do it all in one pass. That's the beauty, I think, of Agda and dependent type programming, that you can have your proofs within the program if they have the same structure. Now this is allowed by the erase types we see with those @0 annotations. We've pushed indices on our simple type. Now it's a dependent type. It expresses bounds, but don't care about the actual verification here. The proofs are carried by the constructors. Here, leaf and right, yeah, in the leaves actually, we check the constraints. And the insert function is a dependently typed function now that makes sure bounds are respected. And we have the code and the proofs living harmoniously on the same level. That's what erasure allows you to do. We compile it and we get the exact same program that we had before. So it's readable, you can communicate with your colleagues in a large Haskell code base. I find it's quite nice as a workflow. All right, so how do we make it so that you can write Haskell like Agda? How do we make it convenient for an Agda programmer in the end? It might be as simple as making lowercase type variables implicit that we are used to in Haskell. This is very easy by declaring that these are general variables to be generalized implicitly. Then we have to find a match between the primitives of each language, so natural numbers in Agda and natural numbers in Haskell, their correspondence between the constructors. But sometimes we don't find the corresponding primitive in Agda. For example, if then else is something we define, we don't have it built in. So then we have to define it, and then our translation procedure has to detect it and say, oh, don't compile that, just use the primitive in Haskell. And you might ask, what if there is an Agda primitive that Haskell doesn't have? Well, we don't care about it because we don't want to cover Agda. So that really makes our tool much simpler to implement, first of all. And then we get to the prelude. Of course, we have to provide the same prelude. We have to port it to Agda. So this is we as agda2hs developers have to carefully rewrite it, make sure that it's correct. This cannot be checked. Or we could do some property-based testing to make sure these correspond, but you still have to trust. It's part of the trusted code base. But we get into the point of the head function. It's a parcel function, but in Agda we never write parcel functions. So everything has to be total for the logic to be sound. And one way you could do that is like using sophisticated techniques like the partiality monad to encode partiality within Agda itself. But this would mean that we have to have this complicated translation and argue that this is correct based on a theory and so forth. But now it's like there is a much more lightweight approach that you can do this. You can say you will not write partial functions in Agda. You will actually write safe total functions with some added preconditions, in this case that the list is non-empty. And then we offer this magic function, which I find beautiful. You can call the error that we normally use in Haskell just by giving the absurd proof. And the definition is quite nice, I think. And then we can actually express that in Agda itself. We say we have reached an absurd case. The list is empty. We have a proof of absurdity. And then we can call error with a proper error message. So I didn't have space to write prelude.head, colons, empty list. And then we get exactly what we wanted. We get, on the Haskell side, a parcel function with correct error messages. And we want the error message because we can feed head whatever we want, right? We can give an empty list. We don't introduce runtime checks, for example. All right. All this is nice. So we've given the primitives, we ported the prelude, and then we go to type classes. Can we find a correspondence? And we also have that in Agda. We have instance arguments which are kind of inspired by type classes and type class resolution. And the correspondence here is that we don't really need a native class syntax or anything. We just need record types, mere record types. These would express the methods as their fields, for example. The instance will be values of those corresponding record types. And constraints in a qualified type, left of the fat arrow, would become instance arguments in Agda with normal arrows. We'll see how that looks like. So let me clarify with an example. We have the monoid type class on the right, and we just have a record with a field mempty and mapend. But look at this wonderful thing. This is my favorite point in this translation, that we can put the monoid laws within our program as erased proofs, express them systematically and type check them, but because they're erased, we get the same type class you would expect. Of course, we have to say to agda2hs, oh, this is a class, it's not a record, because you can also combine the records. And then when we make the actual instance, we give the fields as values of those records. But also we give those proofs. I haven't written them here. They're quite simple for the monoid of natural numbers. And this is what I find wonderful. You write instances that are provably lawful, depending on your type class. And then we used it, as you would expect. The only difference is this syntactic, turning the fat arrow, kind of the extra ink here, you put it here. It's really the same thing. Right, so far everything kind of translates, right? They're kind of the same in those respects, but the languages diverge at certain occasions. For example, term divergence. But in the case of type classes, this would be default methods and minimal complete definitions. So Haskell allows this very practical feature of declaring that there are minimal implementations where you give a subset of the fields. And you can also have default implementations, inefficient default implementations that you might override if you really want performance. And now, okay, I don't want you to understand this thing. It's the most complicated part of this translation. But at least we can, the general idea is that you can express those minimal complete definitions as records again. So we use records again to say that you can have kind of a class that has a strict subset of the fields and then defines the rest. And the only problem is that default definitions are replicated across. And then we instruct agda2hs to say, oh, this is a class, but it also has this extra information. Look at those to make a nice type class as we would expect. And we get exactly what the prelude has. We get what we expect. Then when we use it, of course, we don't need to give all the fields. We do some trickery with record modules. I won't get into that. But the crucial thing here is that our translator has to chase down those definitions of how you use them, detect this usage pattern of sub-records, and then inline it. Because in Haskell, you cannot have kind of importing instances or instances as first-class values, so to speak. Right. And then the great thing about it is that input-output, one of the company that has made one of the largest blockchains, actually uses agda2hs in the wild. It's a prototype, it's kind of a mental experiment, and it's actually used in a slight corner of a huge Haskell code base. Okay, it's not embraced totally. But a bit of background for those of you who don't know, but you should know because it's kind of drastically affected our field. The Cardano blockchain uses a smart contract language called Plutus, based on system F mu omega. They implement, the production code is actually in Haskell. They use a lot of Agda formalizations, so before agda2hs. So James Chapman, one of the co-authors, has really worked on the meta theory of this language. And here we have kind of a more polyamorous scenario, but it's still, I still accept it. And now, how can we use a tool, a lightweight tool such as agda2hs? We have the system F thing, we have types, we want renaming and substitution, and we can actually write it up using some encoding, deep encoding of system F on Haskell here. And now we could use quick check, right? But to use quick check, we need generators for well-typed terms, well-formed types, let's call them here, which is hard, especially if you really want a nice distribution, an efficient rigging strategy. But also, we want arbitrary renamings and substitutions, so it's even harder. It's hard to define, but it's also computationally expensive, because at every time you run the test, you have to wait a bit. So what's the alternative that agda2hs allows? We write almost the same code, right? I hope you agree that this is kind of identical code. But instead of using random testing, sorry, John Hughes, for dismissing your tool, but it's so much easier in this case to write a proof that type is a functor with renaming as the map and a monad with substitution as the bind. This is kind of a page of Agda code. You prove it once and for all, and you're done. You don't have to run anything in your CI tools or whatnot. Yeah, I find this wonderful, and there is a nice analogy with civil engineering, where existing structures are made more resistant to earthquakes using the so-called technique of seismic retrofit by reinforcing their foundations, like just the pillars of the building, right? And in this case, we're doing something similar. There is this huge Haskell code base, and we just take this very important part, like type renaming and substitution, and we just write it in Agda and like secretly inject some Agda into this large code base. If you come from a certain political tradition, you could say that we are seizing the means of production slowly, one by one. Right, so how do we actually implement this? It's quite easy. I welcome everyone to look at the code here in the QR code or the link and see like the actual how the actual translation looks like and how readable it is. I myself was not an experienced Agda developer, and I joined the project because it was very self-contained. Crucially, agda2hs just imports Agda as a library and tells it, oh, take the source program, translate, type check it. This will give us a kind of intermediate representation that has been type checked and carries a lot of type information. And then our translation just takes this intermediate form and spits out Haskell. Crucially, this happens in a type checking monad within Agda. So we have all the information we can ask to normalize stuff, to unify certain things. Yeah, but this backend infrastructure, I guess GHC type checking plugins might be similar in the modularity they allow. And now the serious question of, well, sorry. There is actually a problem with the fact that we are working in this intermediate stage. Because where clauses, for example, do not exist there. Agda has lambda lifted everything to the top level, but we want for the user to see the identical code, right? So we have to reverse lambda lifting. That's the second non-trivial thing we do in our translation. Right, and now comes the question, is this sound? Can we make sure we didn't break anything? First, what do we mean by sound? If I have an Agda file, it type checks, and I compile with agda2hs, it should better be the case that the Haskell thing type checks, and it makes sense. And the semantics are preserved. So if I have a value that I compute in Agda, it should be the same value on the Haskell side. We don't have a formal proof, unfortunately, because it's quite hard. We don't have a specification of Agda, nor a specification of Haskell, unfortunately. But there are steps in this direction. So, for example, there's a project by Jesper Cockx in the Netherlands on formalizing Agda core, Agda within Agda. And this is a step in that direction, and we might take kind of a simpler Haskell-like language, like the type system papers we love to read, and then maybe prove that this translation correct. But we can say a few things about it. We can say, first of all, what do you have to trust? You have to trust our primitives, the porting of the prelude. This you have to check by your own eyes and say, oh, it's the same show instance, and it shows the same thing. Now, all dependent types and like fancy, sexy types are always under an erased annotation, those @0 annotations. So we are sure that we don't leak anything that's not expressible in Haskell. This is enforced by our backend. And of course that the translation of each construct is equivalent. In most cases this is obvious, but there are some that would really benefit from a theoretical investigation. A note here, you might ask what happens with divergence, right? But we only restrict ourselves to total functions, and in Agda every term is strongly normalizing, so we don't really need to care about the bottom and evaluation order. So if you've proven it correct, it will give you the same value whatever evaluation order you choose. But of course, this allows us from working with performance, right? If we want to prove something about performance, it will be some other paper in the future. Right. And by the way, we haven't covered the whole of Haskell features, so we have a lot to do. We have some ideas on how to cover them, like GEDTs, yeah, they're like a subset of dependent types. We would be able to formulate it, I think. Useful language extensions like pattern guards, view patterns, these, I personally believe they can all be done using the powerful with statement in Agda for dependent pattern matching. Some other things really need support within Agda itself, like 32-bit arithmetic. We don't have that, we only have 64. Yeah, you need to first add it and then care about the translation. And the three last items are the interesting ones. Monadic code, how do we deal with it? Do notation, for example. We have some work, but again, we are in this intermediate form and we have to reverse desugaring. Infinite data, we have plans to do it using co-inductive types, and actually the slides are a little obsolete because one of my co-authors actually wrote it down in the past 2 weeks. So we will see a demo at the end of this day where we take the examples Likur was presented and do it in agda2hs. And then the really interesting, like more researchy stuff is how to actually deal with non-termination within Agda. Do we use a sophisticated technique like partiality or the general monad by Conor McBride? And this requires further investigation. And there are some extra goodies like generating runtime checks for all those preconditions we have, just to make sure people don't use the generated code irresponsibly. Or we might be too lazy to prove something, or it might be hard, so then we just postulate it and then generate quick check output, properties that we will random test in our executable stage. And then one quite interesting direction is the inverse, HS to Agda, akin to HS to Cockx, where we take existing Haskell code, since we already have this match between all those constructs, right? And we run it. We run it in the inverse direction, and we get immediately the porting. Yeah, and we want to have more comparisons with liquid Haskell, HS to Cockx, and so forth, more applications. Right. And by the way, this was all done during the past 2 Agda implementers meetings, and I'm organizing the next one in Edinburgh this November, so please join if you're interested in hacking on Agda or you want to cross over. And I would like to just finish with an update on Simon Peyton-Jones' famous slogan. I personally believe if it has run its course, we have we have Lambda in Excel. I think functional programming has come and it will stay. So let's be a bit more ambitious this time and go for dependently type programming. When the doors of perception are cleansed, everything would appear to man as it is, dependent. Thank you.